Hello, everybody. So as the last lecture of the semester, I would like to present simply a selected topic, just as I did for WKB. In this case, I just want to give a very slight overview of scattering theory, just presenting the basic concepts and how the extension from classical scattering theory to quantum scattering happens, and presenting you also what is a cross-section. So that will be the end of the semester. It's a very introductory talk, and essentially it's for you to, enjoy the topic and have a closure in terms of quantum mechanics in this course. So let me share the screen now. Okay, so as I was mentioning, the topic of the talk is basically an introduction to scattering theory and the concept of cross-section. So the quantum description needs some classical concepts, and I want to set up ideas straight, and actually it's easier to start from the classical description because from personal life, that's what you are more used to. So let me get to the classical case first. So this is the so-called classical scattering theory, and you have a very typical problem, as it's kind of like describing the figure. You have a very small particle, and it's directed towards a region of a fixed heavy target that is going to be located at the so-called scattering center. And there is a potential of interaction between the small particle and the heavy target. Okay, so if there was no potential interaction between these two, essentially the particle would pass by and simply ignore it, right? However, there is a potential and there is an interaction between the small particle and the heavy target. So what is going to happen is that the trajectory that the small particle has at, say, minus infinity or infinity, is going to deviate from the case where basically there was no force over the small particle, and it will, at, say, in a way, plus infinity, where I'm using this z-axis, basically be deviated by an angle theta if you compare the trajectories at minus infinity and plus infinity, right? So this is the so-called scattering angle theta. And the parameters of the incoming particle, in addition of this distance b, which is the so-called impact parameter, which is basically the distance that the small particle would pass over the scattering center was there no interaction. It also comes with certain energy. And well, the sketch is basically as it's described in this figure. And before we define which kind of problem we care about in classical scattering theory, there is also some explanation of why we make the assumption of a very heavy target with respect to the small particle, which is that, well, if it's too heavy, basically after the interaction, the recoil of the target, because it's very heavy, will be negligible. So essentially, the target remains fixed in the so-called scattering center. So that's the problem, a sketch for you. This is the typical problem of classical scattering theory. And the essential formulation is like this. So mathematically, given the impact parameter B, you want to calculate the scattering angle theta. Now, that of course depends on the nature of the potential that models the interaction between the small particle and the target. So the goal is essentially to determine the function B of theta depending on the interaction potential. Now, if you want to get some intuition into how this function works, basically, look, if the particle was passing closer to the scattering center by reducing the impact parameter, you would expect a greater deviation because the interaction between the particle and the scattering center will be stronger. So it will deviate more, right? If you make B grow, essentially it will be less influence hand wavy, and so the deviation or the scattering angle theta will be smaller. So that's kind of like the idea. Now, we have sketched the problem in general. Let's do a typical problem, the so-called hard sphere scattering, which is a little bit like when billiard balls collide, but in this case, we have a very small ball, like a marble, and the other is a very heavy billiard ball or even a bowling ball, you know, I mean, just to give a relation between the masses and sizes, etc. So we're gonna assume that the collisions are elastic. Essentially, the particle is a marble and it bounces off elastically from the billiard ball when it collides. So this is the particle coming. Then what you define as the scattering center in this case for the big ball is the center of this sphere. Then B is the impact parameter is this distance between the initial trajectory of the small marble. Then if basically touches the billiard ball, it collides and it deviates its trajectory, right? So this is kind of like the simplest interaction potential that you can think of, especially in classical mechanics, which in history goes even to the studies of Boltzmann's of collisions between particles. But never mind, there is a very small particle and a heavy one. What you can see is that you can determine the parameters of the system simply by trigonometry due to the simplicity of the potential. And there are a couple of things to mention, but essentially, look, what you have as information in addition to the energy of the small particle is the impact parameter B. Then basically it touches the billiard ball here. Then there is an angle between the minus C axis and the point of contact. And that angle is alpha, as you can see. And by a perfect specular reflection, basically the particle bounces off. And it's clear that in a specular reflection, the angle of incidence alpha is going to be equal as the angle to reflection. So basically, that's why you have alpha here. And then if you register what is the scattering angle, if you compare the initial trajectory and the final one, this would be the scattering angle theta, right? So that's the trajectory being deviated after touching the billiard ball. So on one hand, the first relation that you can say is trigonometric, and is that you can relate the impact parameter, the radius of the big sphere, the billiard ball, and then the angle alpha by this trigonometric relation. So B equal to R sine of alpha, and this is just trigonometry, right? Cathode and hypotenuse. The second is basically how to determine this angle theta in terms of the angle alpha. And now I have set up the picture just by complementary angles to show the relation, right? Because essentially the sum of theta and 2 alpha is pi, 180 degrees. So you can put theta in terms of alpha in this form, equal to pi minus 2 alpha. And by simply combining the two relations that you found by trigonometry, and basically you get B as a function of theta, right? So alpha, basically passing in the equation, is this form. It's basically R sine of pi minus theta over 2. And if you use trig identities, you can convert this into R cosine of theta over 2. So there you go. For this very simple potential, you have the relation between the impact parameter and the scattering angle. Now, in this schematic, what I have assumed is that the marble touches the ball. If it's not the case, basically there won't be any interaction because it won't feel the interactive potential, right? It's just hard spheres, just like the interaction only happens if they touch. It's not Coulombic. So there is a condition in terms of, well, if you consider the inverse function of theta in terms of B, you can consider also the case where they do not touch, which is basically the scattering angle will be 0 when B is greater or equal to R, because essentially either it doesn't touch the ball or it just grazes the billiard ball, but it's so-called the grazing collision. And that happens when the impact parameter is greater or equal than the radius of the particle, meaning that it doesn't touch or collide. In the other case, though, when the impact parameter is less or equal to R, you have this relation, which is simply inverting basically R cosine. You have B over R and then R cosine and then a factor of 2. And so essentially in the limit b equal to r, you get 0. So this is continuous in a way. So, okay, for this simple problem where we know if the spheres touch, then you have deviation. If not, nothing happens. It's a very typical problem in classical scattering theory, again, going even to the times of Boltzmann. So it's one of the first problems that you think about in terms of collision between particles with all the assumptions that we have made regarding the difference in mass, etc. But, you know, I mean, this is the schematic of a simplistic problem that happens in a plane because you have assumed a symmetry, basically asymmetrical symmetry. And more generally, in the laboratory, you will deal with problems of this kind. So, which is that, well, you'll have sort of the same problem, but in 3D, right? Because what will happen is that you will have some sort of beam of incident particles, and you will have like some selection of the areas in which these beams impact. And then you'll have some screen which will record when a particle is sensed. And this is again the scattering center where the target is located, or its center. And there will be some influence of the heavy target with respect to the small particles. And they will deviate again with a given angle theta, which is the scattering angle. And essentially the problem we had on the plane reproduces in 3D by simply rotating with respect to this angle phi. So I'm making the same symmetry assumptions of the target, meaning that it has some asymmetrical symmetry with respect to the z-axis. And now I simply, basically I rotate this picture in a way, but I have different particles and I have a control on where they enter by means of this basically planar coordinates, which are somehow spherical too, right? So anyways, I'm gonna define some concepts as in the figure. So this d theta patch is gonna be called the cross-sectional area. And where you impact in this hypothetical sphere of radius 1, let's say, is gonna be the solid angle d theta. And again, you let particles come in this patch of cross-sectional area d theta. So that's where the particles incident enter the picture. And then after interacting with the target, they will scatter into this infinitesimal solid angle. So right now, I don't have basically a single particle, but I have a certain stream of particles entering through this patch. And then they touch the sensor in this solid angle. Intuitively, of course, if you make the area of the patch bigger by increasing the sigma, you'll have the omega increasing. Sorry if I changed the names. I apologize. I'm thinking of many things at the same time while I'm saying this. So you have the d sigma and then the d omega. And there is, of course, a monotonic relation increasing as you increase this the area of this patch. You'll increase the solid angle where the particles touch the sensor. And we have to make another definition for the case of classical scattering theory, which is actually a concept that we'll extend in the quantum case. So you're gonna define the differential scattering cross-section as the factor of proportionality between d sigma and d omega. And we're gonna use the name d as a function of theta. Basically, given the asymmetrical symmetry we have assumed, this proportionality factor will only depend on this theta, but, excuse me, you'll see also why they relate. And simply differential version of this equation is by passing the d omega to the other side. And so you have d sigma equal to d of theta d omega. So how do we relate this new concept of the differential cross-section with what we saw as impact parameter and scattering angle? So, well, again, using certainly planar polar coordinates and basically spherical coordinates. For d sigma, given that you have b as in this figure, basically you have db, so which is this part, and then b d phi, which will make this side. So that's how the area d sigma of the cross-section patch will come. And for d omega is again a trigonometric relation, which you can actually see from here. Basically, you'll have, of course, the d theta, and then sine of theta d phi, right? So still you have the variation. Basically, the d phi is related to the variation that becomes or makes the problem go from 2D to 3D. And then sine of theta d theta is basically reproducing this side. So, well, again, by conceptualizing how the 2D picture became a 3D picture, essentially we are rotating by means of this angle phi. And you can simply think that each scattered particle remains in its own plane of interaction. By making this rotation, you're simply considering different cases and different planes. And that's what generates the 3D picture. So, well, let's see, let's continue. We are close to basically relating the concepts. And well, if you remember, basically we define the differential cross-section as the ratio between d sigma and d omega. So if you compute the ratio with the trigonometric relations that I just gave you to the coordinate system and the symmetry assumptions of azimuthal symmetry with respect to the axis C, basically you have to just plug in these two, right? So if you substitute, you have the ratio b over sine of theta, then there will be an elimination of this d phi, which occurs in both. And then the reason we put this absolute value is because we have pointed out that basically b decreases by increasing theta, but we know that sigma increases with omega, or d sigma increases with d omega. So there has to be a change in sign from decreasing relation to an increasing one, and that's why we get the absolute value. So far, this is cool because we have been able to define this proportionality factor given the assumptions in our problem by the information we would have if we solve the scattering problem, right? Because, okay, b would be a function of theta, then sine of theta, okay, is given, and then this is the derivative of the function that you were to find had the potential. So for example, for the case of the hard sphere scattering that we were studying, we can continue and find the differential cross-section. So what is the differential scattering cross-section in this potential? Well, the result that we found before was, of course, this one. B is equal to r cosine of theta over 2. And if you compute the derivative, you have simply this, of course, this factor of 1/2 coming out and the minus. And then by using this formula, you have B divided by sine of theta. So far, so good. Absolute value of dB of d theta. So that's why you have this. And then you have, by taking out the r, you have r squared over 4 divided by sine of theta. And what you do is, well, here you have 2, but you multiply by a factor of 2 to basically get the same, because you already know what you're going to get. Basically, you have sine of theta over 2 cosine of theta over 2. And so you know that if you multiply by 2, you actually get sine of theta. So that's why you do this multiplication in advance. And basically, this is 1. So that's why the result is r squared over 4. Now you have to think of a couple of things. Well, the first one is that this is a case where actually the differential cross-section does not depend on theta. This is because of the particularities of this simple classical example of hard spheres. This doesn't happen in general. This is just a feature of this simple case. This is unusual. The other thing, which we'll see basically a little bit in a second, is what does this r squared over 4 represent? But well, we'll hold into that. Let's continue with the definitions. We had talked about the cross-section area for the patch, the theta, but if we care about the total cross-section, basically, we'll define it as the integral of the theta over all solid angles. So just 1 second. Sorry, I got distracted. Why do we define this? It is because essentially when you care about the I'm sorry, I got very distracted with this thing. Look, essentially you define it, the total cross-section area, because of the following. Because you know that the relation differentially is that d theta d omega is basically going to be the d sigma, So if you use the definition, of course, you had the sigma over the omega, multiplying by the omega, then you get the d sigma. So of course, this is the total, so the integral of d sigma is, it's even natural in a way, and also why you come up with the total cross-section area. In fact, the way to kind of like go from here to here would be precisely starting here and then get to this part. But okay, this is the definition, and so far so good. So this is where we come up with the interpretation, right? Because, okay, sigma can be interpreted now as the total area of incident being scattered by your target. And what do I mean by that? Basically, we have the patches d sigma, and then we integrate over basically the theta and the omega, or integral over the sigma. It's basically considering all the area in which the particles enter if they are some beam. So that's what makes sense from this calculation. Now, basically, that's why it's called a total cross-section. But if we consider this computation for the particular case of the classical scattering of hard spheres, we have to plug in our formula where we already noticed that this was independent of theta for this case. So you have integral of r squared over 4 the omega, which comes out, and then you have the integral of the omega. And this is basically an integral of a solid angle, but we'll have to be a little bit careful. I'm using an absolute value here. And integrating appropriately over this, basically I will get a factor of 2 pi from the azimuthal angle, and then 2 cosine of theta from 0 to pi over 2, where I actually hit the sign. Basically, I, by symmetry, made it twice the integral from 0 to pi over 2, then I'll get a minus, and then basically the minus made me flip the limits of integration. So that's why I get this. And well, if I evaluate, basically, this will become 4 pi. There's a cancellation with this 4, and then that's why you get pi r squared. So how do we interpret this result for our hard spheres case? This actually makes a lot of sense, because this is the cross-sectional area of a circle of radius r, right? So basically, what would happen is the following. You're entering here, and this is the total cross-section area that you see from afar. Then that's how the particles are entering. And again, basically, I will actually change this of the circle. Sure. And then just some explanation. Okay. So basically, particles inciding in the area of pi r squared in the circle of radius r will get around the target. And then outside of that, you'll miss the target. So if you go back to the problem of the hard spheres, this is what you're looking at, right? So basically, you're entering here. You only see this area of pi r squared when you make the cut of the orange by basically looking from here, and that's what you'll see. Actually, maybe the explanation of the sphere was better. Yeah. So, okay. Yeah. So, okay. Basically, if you incide within this area of pi r squared, the area of the circle that you see from afar in the hard spheres problem, you'll get the target, but if not, you'll miss it, right? So that's the so-called hit or miss situations. But this illustrates, at least for this simple example, the physical interpretation or the geometrical interpretation of the total cross-section area. Now, we studied a very simple problem of hard spheres where you either touch it or you don't, but this same terminology can be used for the so-called soft targets. You know, a simple example would be basically a Coulomb potential where, you know, you have a heavy nucleus being the target, and then you have a proton, right? So there is some attraction, some electric interaction, and it's not that you touch it or you don't, but simply the Coulomb potential is effective and will impact or interact with the particle, even if they do not touch. That's the whole idea of the Coulomb potential. It's an action at distance. Actually, the Coulomb potential is very strong in that case, but the point is that they do not need to touch in this sort of hit or miss case as for hard sphere potentials. But you can use the same terminology as a differential cross-section area, the cross-section patch, etc., etc. because problems can be solved like that. Essentially, it's a little bit like a black box problem if you think about it. Essentially, if you go from here, right? You have impact parameter, potential, scattering angle of deviation. Here's a concrete example of where you see how the machinery inside the black box works. But here, I mean, in principle, we're not making any assumptions. We just have the detector, then you have the particles, and then they interact in whatever way the potential between the particle and the target demands, and then it deviates, right? So that's why we can operate in this sort of black box approach for other kinds of potentials which are related to soft targets. Anyways, extending the ideas from the simple case to the lab, etc., is that usually on the lab you'll have like some stream of particles or some incident beam. So it's not as simple as one or just you know, rotating one case each time. You'll have many of them, and well, this is kind of like some sort of current, and we're going to use actually the term luminosity. Basically, when you have a beam of incident particles and you assume that the intensity is uniform, which experimentally you'll have some control over that, particle physicists call it luminosity, and we're going to define luminosity as the number of incident particles per unit area per unit time. So it kind of makes sense, right? Because what you have is essentially a flow, have some stream of particles, and per unit area, of course, is related to the sigma. Per unit time, it has to do with the velocity of the stream of particles or the incident beam. If I go back to that, I can have a relation, right? Because the number of particles per unit time that enter the area is simply basically multiplying L by the sigma, because, okay, this was per unit area per unit time. If I multiply by area, I get by unit time. So this is the end. And I'm gonna use the relation that I know between the sigma and the omega, which is with the differential cross section. That's why I have the theta, the omega, and then I have the n equal to L times this. And well, this is nice because now I can have defined the differential cross section as the ratio of the derivative dn over the omega divided by the luminosity. And what you're doing is essentially normalizing by the uniform luminosity that you get by assumption, right? And the reason this definition is useful is because these are quantities that are experimentally measurable in the lab. So if you were an experimental physicist, this is what you would use to put the problem in mathematical terms. And so, okay, this is the solid angle. This is basically the number of particles that enter per unit time. And then you have the luminosity of the incident beam and you normalize it, right? So basically, this is how you would get the differential cross section. Now, how does this relate to quantum scattering theory? Well, not all concepts are extendable because essentially what you have is, what you have now in quantum scattering is wave scattering, because you have a wave function, a matter wave you want, but still it's a wave. But the concept of differential cross-section actually will be useful and it will still appear in wave scattering. And that's why we spend the time in the classical case. So in any case, I mean, again, this is basically scattering of waves due to the wave function in quantum scattering theory. And the theory is actually not so different for wave scatterings in general if you have waves in water, etc., etc. But in any case, this is the mathematical formulation. You think of an incident plane wave that is traveling along the z direction in this form. Basically, you have a planar wave, e to the ikc, where of course you define the direction of propagation along the z-axis. So this is the incident wave, which is a planar wave in the mathematical form that you see. And again, we operate in this some sort of black box approach where you don't know exactly what's the type of interaction. Perhaps you're not given the potential yet, but what you'll see is that after interacting with some sort of target, which is located or centered at the scattering center, the wave, in this case, a matter wave if you want, or the wave function of the quantum problem, will emerge as a spherical wave. So basically, you have the planar wave, this is the incident wave, then you interact with the target with some sort of potential, and after the interaction, you emerge as a spherical wave, which intuitively, it's what you would expect, actually, right? I mean, by extending the concepts of incident particle and deviated particle to an incident wave and the scattered wave. So the interaction will make the wave become spherical in a way. Now, this is hand wavy understood, but how to pose this mathematically in terms of the solution of the Schrodinger equation, right? So perhaps we don't know the whole details over here because it might be too complicated given the potential or the features of the particle. But you know that at infinity, basically what you will see is two components. So at infinity, in this polar coordinate description, what you'll see is the planar wave on this side, and then basically the spherical one. So you'll notice that there's a factor of 1/r because this has to do with essentially probability conservation. So the first point is simply, I just want to point out, this is the behavior at infinity. This is the planar wave component of the incident wave. And this is the component of the scattered spherical wave. Now, you have a factor f of theta. This is basically to indicate that at different angles in this description, you might have different probabilities of scattering. And again, this factor 1/r, maybe you have seen it before in your quantum course, maybe not. It is because you'll have some probability conservation. So the wave is expanding spherically. And so it needs to scale as 1/r², the probability. That's why you have psi squared, norm squared equal or proportional to 1/r², so that you conserve probability in the spherical flow, right? It's when you have a spherical wave propagation. And well, I mean, this was just a mathematical justification of this polar coordinate description where you're given the z-axis in terms of r and theta, where of course the angles are either 0 or pi, and then you get plus minus r for this, but this is just mathematical. So, okay, you have the incoming matter wave, as I mentioned, and at infinity, basically, you're going to assume that the potential goes to 0. So basically, all the energy is kinetic, and therefore you can relate the wave number of the planar incident wave with the energy of the wave function. So that's why you have this relation of the wave number in terms of kinetic energy, which, I mean, if you pass h bar to the other side, is basically some sort of quantum momentum, and you have the typical relations between energy and kinetic energy when there's only kinetic energy and not potential. So anyways, just commenting that usually F would depend on theta and also on phi, but you're assuming a simultaneous symmetry, so that's why this is reduced to a function of theta. So basically what I want to point out is that in the quantum case of quantum scattering theory, where you are analyzing scattering of waves, the idea is to find out what is this factor, which is the so-called f of theta, which is the so-called scattering amplitude, because that will give you the probability of scattering in a given direction. So if you see the schematic, basically, if you change the angle theta, maybe the probability is lower in different angles, you know? So that depends, of course, on the features of the potential of interaction. But I mean, it kind of makes sense to pose this solution and then to put as the goal to find this. And this is, or this factor of theta is the one that will be connected with the concepts of classical scattering theory. And well, we are going to pose a problem mathematically as some sort of flow of probability or a flow or of a matter wave. So you don't have particles anymore. You have waves, even if there are waves of matter, but you have to think in terms of flows. So basically, we'll use the differential cross-section still, but in this new framework of waves flowing. And so you have the probability of the incident particle wave traveling at a given speed b that will pass through a given area, say the sigma time dt. So looking at the picture, this makes sense because what you'll have is a hypothetical cross-section area, the sigma, then the wave will travel, so it will basically enter this area for a time dt with a given direction, and then you have the travel distance in a time dt is b dt, if b is the velocity, and how much basically matter wave or probability traveled, right? So, well, this is basically some sort of fluid equation, but now you have a fluid or flow of probability, and the probability traveling at the speed b passing through the d sigma patch at time dt is basically calculated this way. So this accounts for the probability, taking it as constant in this volume element, and then the actual volume of this hypothetical geometrical object, right? So on one hand, because we're just talking about the incident wave, this is only related to this part. So that's why you have norm of a squared and this part, because this is norm one. And then you have BDT accounting for this side, and then the area of this cross-section area, DC. So this is basically how much probability flew in this patch for a unit of time. Now, we'll do the same analysis where, again, I emphasize this is the volume. Well, this picture presents the volume of incident matter wave passing through the area d sigma for a time dt. And you'll also have probability conservation, right? I mean, so essentially what you care is not now on the incident wave, but you care about the scattered one. So what you'll have is, again, this same analysis, basically the Froth probability, where you have the magnitude entered in the differential volume element, but now you'll have this part of the wave for the scattered wave. So you don't care about the incident, you care about the scattered one. And well, basically, if you care about the probability, this is going to be squared, and this is norm one. So that's why you have basically norm of a squared, norm of f squared, divided by r squared, and then you got some of the other elements. But now the patch, well, this was an inadequate patch because it was reflecting this path along a given direction. But the patch that you need now for the spherical propagation is one that considers precisely the spherical propagation of the wave. And so that's why you have r squared and the solid angle. This would be basically, if you think of the Jacobian in spherical coordinates, we're just missing a dr, which is in the direction which the wave is propagating, but r squared d sigma is basically the Jacobian in spherical coordinates. So this is a patch of the traveling of the wave in like this, essentially. And you'll have the r squared factor basically normalizing by the stage in the wave propagation that you are, because your wave will expand in a bigger and bigger radius. So anyways, if you get the relations by probability conservation, basically you equate this term to this other term. So what you'll have is some elimination. Actually, this r squared factor is quite convenient because that's the whole reason we chose the 1 over r in the wave function, that you would have this cancellation. And so you'll have that the sigma, in this case, basically the area of this patch, is basically equal to norm of f squared times the omega, where the omega is the solid angle. So actually you get a relation as in classical scattering theory, but now in quantum scattering, where you have the differential cross-section, which relates the area basically of the patch d sigma of the cross-section with the solid angle d omega. We're still going to define this as the theta for the purposes of this lecture. And this is simply norm of f of theta squared. So f depends on theta in the simplistic feature of the problem we have thought. And again, we stress that the differential cross-section is basically a quantity of interest for experimental physicists. And what we have shown is basically how this experimental quantity is related to the math solution of Schrödinger equation, right? So what you would like to know, once you actually know the exact potential that you're dealing with, is basically norm squared of f of theta, because this factor determines the probability of scattering along this direction of angle theta. So with this relation. So, okay, this is basically the simple presentation of classical and quantum scattering theory and how the concepts relate, especially the concept of differential cross-section. Well, I just wanted to mention that basically possible techniques for calculating this, because this is the whole goal in quantum scattering theory, is that you can use two techniques. One of them is called partial wave analysis, and the other is the Born approximation. I won't touch into that. Maybe you'll learn this in another quantum mechanics course in grad school. But for the moment, this is all. I just wanted to complete this topic. And Griffiths was the reference, as you can see from the many diagrams that I included, that are taken from the book. But okay, this is the last lecture of the course. I really hope that you liked the material and that you found quantum mechanics in a second view very interesting from the point of view of basically different mathematical methods to study more complex problems in quantum mechanics, and essentially the interaction with some physics concepts in, time-dependent perturbation theory and probability of transitions. But for the semester, this is all for my part. This is the last part of material that I will touch. And I must just say that it has been a pleasure to give you the material and teach you this course, even if virtually in an asynchronous modality. I hope that you have enjoyed it as much as I enjoyed presenting you this material. And well, thank you again for the opportunity to be your instructor this semester. And I wish you all the best in what comes in terms of the final exam. So best of luck, and all the best for the rest of the end of the semester.